Today we're discussing section 6.1 on systems of equations in two variables. So here are our objectives. And starting right off with the definition, a system of equations is a set of two or more equations that are considered together. So a solution to that system are going to be two variables, x and y, that make both equations true. So if you see this example down at the bottom, we have x plus y equals 5 and 2x minus y equals 1. And the solution to that system is going to be an xy pair that satisfies both. So we're looking for an xy pair that satisfies both. And we'll have three different methods today for being able to solve these systems. So method one is graphing. We're actually going to solve this system of equations by solving each equation for y. So we have a y equals to plug into our calculator. We will then graph both those equations and find where they intersect. And we'll use our calculator to actually solve for that intersection. So starting off, we have x plus y equals 6 and 2x plus y equals 0. So we're going to take the x plus y equals 6. We're going to subtract x from both sides to get y alone. We're looking at 6 minus x on that one. And then we have 2x plus y equals 0. So we subtract 2x from both sides. Y equals negative 2x. That gives us our two y equals. Now we're going to turn to our calculator to graph these. So we go to our y equals and we have 6 minus x as the first one and negative 2x as the second one. When we graph them, we can't quite see where they're intersecting, so let's zoom out on our window. Count by 2, negative 20 to 20. Again, count by 2, graph. And there is our point of intersection in that upper left quadrant. So now we'd like to be able to solve for that intersection because that will be the xy pair that satisfies both equations, right? We need an xy point that sits on both lines, and that is going to be our point. So we go second, calculate, and we go down to intersect. And now it asks us to identify the first curve, which is already highlighted for us, so we hit enter. It asks us to identify the second curve. We hit enter one more time, and there it solves the intersection for us, negative 6, 12. So that's probably our easiest method for solving for the solution of equations. Now back to our slides. We got negative 6, 12. So we got negative 6, 12 as our solution. And you could plug it back in. If I plug in negative 6 for x and 12 for y in both equations, it should be correct. So whenever you have a system with two equations and there's just two variables, x and y, three things can happen. We either get that the lines intersect at a single point, like we saw in that first example, we get one solution or one point. If the lines are parallel, so when we look at the graph, they actually go parallel together, like that. That is when we say that there is no solution because there's nowhere where the lines intersect. That system is inconsistent. We could also have that the lines actually are the same. So one is just a multiple of the other, but that they completely overlap. And that is when we say that they have infinitely many solutions. That is also a system that's called consistent, meaning it does have a solution, but we say that the equations are dependent. And for that first example, that first possible outcome, we say the system is consistent because it has a solution, but we say the equations are independent because they're truly different. So they're independent. So this is what the graph looks like for each of those. When we have exactly one solution, they cross at exactly one point, and we say that is a consistent and independent solution. When we have parallel lines, that means that they have no common points, so there's no solution there. That's what we call inconsistent and independent. Now, when the lines actually overlap and they are truly identical, we say it's consistent because it has a solution, but we also say that the lines are dependent because one is a multiple of the other. So those are your three possible outcomes. No matter what method you're looking at, we will actually see the algebra for each of these methods, each of these outcomes moving forward, but the graph will always look like this. So coming to our next method, the substitution method. See, we like to be able to do things algebraically because graphing doesn't always give us the exact answer that we're looking for. So what we're going to do with the substitution method is we're going to solve one of the equations for one variable. I typically like going for a y equals just because it's natural. We're then going to substitute that expression into the other equation, and we're going to solve that one variable equation now. It's going to be a linear one that we know how to solve. Now we're going to take that and plug it back in to find our other variable, and then we have both our solutions, both our x, y values. So we can check always by plugging them back in, and I highly recommend always checking your answer with these because why not? You can always make sure that you're correct. So we have this system, solve the system by substitution. We have x minus y equals -3 and 6x plus 9y equals -33. So let's take that x minus y equals -3, and we're going to solve for y. So I'm going to subtract x over first, and I get -y equals -3 minus x. Now I divide by -1, and I get y equals 3 plus x. Awesome. So now we're going to take that y, and we're going to plug it in for this y in this second equation. So we do 6x plus 9, and now here's where we're substituting, right? We know y equals 3 plus x, so we plug that in for y here, -33. So now we have an equation that only has x's in it. So we know how to solve for this. We take 6x plus, and then we distribute our 9, so we have 27 plus 9x equals -33. And now combining like terms, I have a 15x with 6x plus 9x plus 27 equals -33. I subtract 27 from both sides, and I get 15x equals -60. And so therefore I can divide by 15 and I get x equals -4. Now, we always have y in terms of x because of the way we did this. So we know y equals 3 plus x, or 3 plus -4. So that's -1. So there's our xy pair, -4, -1. And you can plug those back in and check that we do in fact get the answer that we're expecting. So that is what we call a substitution. Now, we got it down to a single point. So notice this is our consistent and independent solution. The system, we say, is consistent and independent. Now let's see the next example where we're actually going to have an inconsistent or independent answer. So we know we shouldn't get a solution here, but let's see what actually happens with the algebra. I'm going to take y minus 7 equals 2x and solve for y. So we add 7 to both sides, and I get y equals 2x plus 7. And now we're going to plug that in. So we're substituting that value for y in the other equation, right here in this y. So we're going to take 2x plus 7, and we're going to add 7 and see if that equals 2x. So that gives me 2x plus 14 equals 2x. Now, whenever I have x's on both sides, I prefer to have x's only on one side. So I'm going to subtract 2x from both sides. But look what happens. I get 14 equals 0. And I lost all my x's. But I ended up with something that is completely untrue. 14 cannot equal 0 ever. So this is when we know that there is no solution. Here, if you graph these two lines, you would find two parallel lines. And in the algebra, you end up with some number equals another number, which clearly is not true. That's when you know it's no solution. Now let's see the third case when we actually have a consistent system, which actually has solutions. However, it is dependent. So one of these is actually a multiple of the other. So let's do substitution still. We're going to take that y plus 5x equals 2, and we're going to solve for y. So subtract 5x, and we get y equals 2 minus 5x. Now I'm going to plug that into my other equation. I have minus 10x minus 2. Here's where I plug in my y, 2 minus 5x. And that equals negative 4. So I have a minus 10x, and then I'm going to distribute. So I have a minus 4 plus 10x equals negative 4. But see, what happens is my minus 10x and the plus 10x, when I combine those two, I'm left with negative 4 equals negative 4. Now, that is true. That's always true. And that means that my solution is all values of x. So my solution I could write as x 2 minus 5x, like that. Essentially plugging in the 2 minus 5x for the y value, right? It's any combination of x and 2 minus 5x that will make it work. And that is actually your answer. So it is that these two are the same lines. That's what this implied, same lines. When you graph them, they'll actually completely overlap each other. And we saw that it reduced down to x is falling away, but we're left with a number that does in fact equal the other side. So that's what a consistent and dependent system looks like. Now we have our next method, the elimination method. It's especially useful when neither equation is really easy to solve for a variable. Sometimes it just kind of comes out at you as a little bit easier. So what we're going to do is actually add and subtract the equations together. And hopefully it removes one of the variables, like they kind of cancel each other out, and you're left with something with just one variable. Typically with these, we like to get it to one variable so that we actually know how to solve it using our standard algebra techniques. So with these steps, you're going to write both equations in our standard form, putting x's and y's on one side. We often have to multiply one or both of the equations by some number, maybe the coefficient in front of one of the variables, so that they are opposite signs. You'll see an example of that. Then we're actually going to add the two equations together and solve the resulting one variable equation, and always check your work. So let's see our first example of this. So here I see x minus 2y equals 9 and 2x plus 5y equals negative 45. It wouldn't be nice if I had a negative 2 in front of my x so that I could just cancel my x's when I add these two equations. But I can't just throw a negative 2 in front of the x. I need to multiply the entire top row by negative 2. When we do that, we get negative 2x plus 4y equals negative 18. So we've carried that minus 2 across the entire row. And then we leave the second row alone. Now I can actually add these two equations and see what happens. See, if I get a negative 2x plus 2x, I get 0. And now when I have 4y plus 5y, I get 9y. And when I do negative 18 plus negative 45, I get a negative 63. So I've reduced these equations to just look at 9y equals negative 63. And if I divide both sides by 9, I get y equals negative 7. Now I can take that y equals negative 7, I can plug it back into either of the two equations, and I can solve for x. So if y equals negative 7, I have x minus 2 times negative 7 equals 9. That tells me x plus 14 equals 9. And if I subtract 14 from both sides, I get x equals 9 minus 14, negative 5. So our point is negative 5, comma, negative 7. And as it says at the top, this is a consistent, meaning it has a solution, an independent system, meaning it has a single solution. And we found that single solution. So most of the time, if it's not specified, it's up to you whether you want to use substitution or elimination to solve the system of equations. Now let's see what happens with elimination on an independent, inconsistent system. See, I have a 6x up top and I have a 2x on the bottom. And it sure would be nice if that 2x were actually a negative 6. So I'm going to multiply this whole row by negative 3. I'm going to leave the top row alone. And on the bottom row now I have a negative 6x plus 3y equals negative 21. When I add these two equations then, I have a 6x minus 6x, that gives me 0. I have a negative 3y plus 3y, well that gives me another 0. But when I add those two, I get 2 plus negative 21, that's negative 19. But I can't have 0 equals negative 19. That's not true. Therefore, no solution. So that's what elimination looks like on an inconsistent system that won't have any solutions for you. You basically get it down to 0 equals a number again, and that's a problem. So we're done here. Now for our third case, we're going to see a consistent and dependent system here. So again, I'm going to multiply the bottom by 2 here. I want to make that, oh, hang on, let's go back for a second. I want to line up my x's and y's, and notice my x's and y's are in 2 different orders. So I want 2x minus 6y equals 10. That's really the top row. And the bottom row is 3x minus 9y equals 15. Now, I'd really like these to both match, maybe get to a positive 6x and a minus 6x. So this is the case where we actually have to multiply the top and the bottom by a number. So my x's and y's line up, so therefore I want the coefficients to line up as well, at least in the x's. So I'm going to multiply the top row by a negative 3, and I'm going to multiply the bottom row by 2. That's going to give you a minus 6x on the top row and a plus 6x on the bottom row, and that's what we're looking for. So if I carry this out, and I'm going to actually carry out that multiplication, I have a minus 6x plus 18y equals minus 30. And then I have a 6x minus 18y equals 2 times 15, positive 30. And now see what happens when I actually add these two rows, when I add these two equations, which are multiples of our original equations. I get 0x plus 0y equals 0. And we can have 0 equals 0, therefore the system is the entire line, all x values. Because this system is dependent, they are the same lines. So any x value will work. There are an infinite number of solutions here. Now, we're going to look at a few applications of this type of work. So when we look at the word problems here, we're going to identify and assign our two variables. You could either call them x and y, or you can pick letters that make sense for the problem. We're going to translate the problem into equations then, and then solve the given system using substitution, graphing, elimination, whatever you prefer. Then typically we'll want to answer the question in a complete sentence, and then check that the answer makes sense in that context. So here is our first application. We have 2 common names for the streets, which are 4th Street and Main Street. We have 16,413 streets bearing one of those 2 names. And we know that there are 413 more streets named 4th Street than Main Street. How many streets bear each name? So I'm going to call F equals the number of 4th Streets. And I'm going to call M the number of Main Streets. Now, we know in total there are 16,413 streets bearing one of those 2 names. That means that when I add the 2, F plus M, I must get 16,413. So that's our first equation in our system. Now the other piece of information we're told is there are 413 more streets named 4th than Main. So I should have then that 4th is Main plus 413. Right? There are 413 more streets named 4th than Main, so I need to take Main and add 413 to it to get to the bigger one of 4th Street. So these are our two equations. Now we're going to use substitution to actually solve. The reason I like to use substitution is because we already have f equals as one of our equations. Therefore, it's really easy to go ahead and substitute it back in. So we're going to take this and substitute it in for f right in there. So we get m plus 413 plus m. So this is where we did our replacement for f. And that equals 16,413. So we've taken that first equation and we plugged in m plus 413 in place of f. Well, now this is something with one variable that we can actually solve pretty easily. If I combine like terms, I have 2m plus 413 equals 16,413. Which then, of course, I get 2m equals 16,000 and m equals 8,000. So we have one of our variables, m equals 8,000. Now we want to go back for our other variable. See, we know that f equals m plus 413, and we now know m is 8,000 plus 413. So we know f is 8,413. And we have our two numbers that we were looking for. If we wanted to, we could actually write this as a sentence saying there are 8,000 streets named Main Street and 8,413 streets named 4th Street. And that's what that would look like fully complete. Notice these two numbers do in fact add to 16,413. Now on to our second application. So this one says a few years ago, a total of 2,689,000 people lived in the metropolitan areas of Las Vegas, Nevada, and Sacramento, California. Sacramento had 285,000 more residents than Las Vegas. What was the population of each metropolitan area? So I'm going to call L as the population of Las Vegas, and I'm going to call S the population of Sacramento. Now, the first thing says a total of 2,689,000 people live in the two areas. That means that L plus S equals 2,689. The other piece of information we're given is that Sacramento had 285,000 more residents than Las Vegas. So Sacramento is Las Vegas plus 285, right? It has 285,000 more residents. So we have our system of equations, and one of them is an S equals, so we're going to use substitution. We're going to take that L plus S equals 2,689, and we're going to plug in what we know S equals. So we're going to take this and plug it in for S. Then we get L plus 285 in place of S equals 2,689. Well, that tells me 2L plus 285 equals 2,689. And if I subtract 285 from both sides, I get 2L equals 2,404, which of course then bringing it back up, L equals 1,202, just dividing by 2 on both sides. So now that is going to be our population for Las Vegas. We want to go back and solve it for Sacramento. And remember that S equals L plus 285. So that's 1,202 plus 285. If you put that in a calculator, you get 1,487. So we found our population of Sacramento and our population of Las Vegas, and these both are in the thousands as our units. Again, if you wanted to write down a full sentence, if you were asked to maybe on the final or somewhere else, we would say the population of Las Vegas is 1,202,000 people, and Sacramento is 1,487,000 people. On to our third application. So this one says the average apartment rent in country A is $1,340 per month. Jacob has an apartment in city B and one in city C. The total monthly rent for the two apartments is $4,895. The rent in city B is $1,161 less than the rent in city C. Find the rent for each apartment. So this is an example where we actually have a little bit extra information here. See, we care about the rents between city B and city C. And this whole country A average actually doesn't play a role whatsoever. So first we write down that B is going to be the rent in city B, naturally, and C is the rent in city C. Now it says the total monthly rent for the two apartments is $4,895. That tells me B plus C add to $4,895. We also know that B is $1,161 less than the rent in city C. So B is C minus 1,161. And there is our system of equations. So we're going to take that B equals and we're going to plug it in into our first system, again using substitution. So essentially we take this and we plug it in for B up here. Then we get C minus 1161 plus C equals 4895. And this is where we plugged in B. We could put in parentheses, but it doesn't matter too much really. So if I combine like terms here, I have 2C minus 1161 equals 4895. That tells me that 2C equals 6,056. Again, adding 1161 to both sides. If I divide by 2, I get C equals 3,028. And so to solve for B, well, that's C minus 1161. And so if I plug that in, 3028 minus 1161, that is 1867. So we have the rent in city C and the rent in city B. That's what we were asked for this problem, was to find the rent in either. Your sentence here would be the rent in city B is 1,867 and the rent in city C is 3,028. And you can check those two do in fact add to 4895 and B is 1,161 less than the rent in city C. So another great application of a system with two variables. On to our last example. This one says you invested $7,000 between two accounts paying 4% and 5% annual interest respectively. The total interest earned for the year was $330. How much was invested at each rate? So I'm going to call A the interest or the amount for the 4% account. And we're going to call B the amount for the 5% account. Now I know the two amounts must total 7,000, right? So I know A plus B must total 7,000. I also know 4% of A and 5% of B totaled to $330 because that's how much interest was actually earned that year. So I get 0.04A plus 0.05B equals the 330. All right, so now this is a good candidate for maybe elimination, but to keep things simple and systematized, let's go ahead and keep using substitution as our method here. With substitution, we would want to solve for one of our variables. So from here, if I subtract B to the right-hand side, I know A equals 7,000 minus B. Therefore, plugging that into my second equation, I get 0.04 times A, and instead of A, I write 7,000 minus B plus 0.05b equals 330. So nothing else about the equation changed. I just plugged in what I know A equals. Now if I distribute my 0.04 to both terms, I get 280 minus 0.04b plus 0.05b equals 330. And so combining like terms again, I have 280 plus 0.01b equals 330. Notice I can combine those two b terms. Now I subtract the 280 over and I get 0.01b equals 50. 330 minus 280. Now all I got to do is divide by 0.01 and I get b equals 5,000. 50 divided by 0.01 is 5,000. So going back for A is just 7,000 minus B, which of course now we know is 7,000 minus 5,000. So A equals 2,000. Notice those two do in fact add to 7,000 in total. And if you check and take 4% of the first one and 5% of the second, then you'll get your your interest in total being $330. So to sum it up in a sentence, the amount invested at 4% is $2,000 and the amount invested at 5% is $5,000. So that's it for these problem types. Again, these are all word problems that had to be translated into a system of equations, and then we use our graphing, elimination, or substitution from there. So that's it for 6.1, and please reach out as always if you have any questions.